Hello, welcome back. So today I'm going to do something a little more serious. So I'm going to be talking about numerical differentiation. So what is numerical differentiation? It's actually the differentiation of mathematical functions that we perform using numbers. So what it means is we first convert the functions to numbers, and how we do that is by evaluating the functions. So I'm going to show you first what I mean by function and how you can easily represent that in MATLAB, and then how you evaluate the function, that is converting the function to the numbers. Then before we now talk about the differentiation. Now let us start with a simple function. For example, I'm going to use a function, say h of x. So let me insert from equation. So I have h of x equals squared. So cos square of x. So how do we do this in MATLAB? So we use what we call a function handle. So to use a function handle, let's say you want to assign that to h, so h equal to at. You use the at symbol, and then you list your variables. So here I'm using just one variable squared. So x and then cos x squared. You don't put the square before the x. This is how you write it when you are programming. Then I can evaluate this as any value. For example, let's say I want to evaluate the value. I want to know the value of h when x is 2. So I'm going to say h and I pass 2 to it. So this way, MATLAB is going to replace the x in h with 2 and then run the calculation to tell me what the value of x, what the value of h is when x is 2. So if I might want to know another value, I say maybe what is h when x is 5 or what is h when x is 20. And then if I run this, I'm going to get the value of h for all those inputs. So that is how to evaluate a function. I mean, at different values. It's just pretty simple. But then x can be a vector or a matrix. But we'll talk about that and the modification that you need to do to h for you to be able to handle that in another video. But for now, this is how to evaluate a function. So we will move to the next thing that we want to discuss. How do you perform numerical differentiation? But before we do numerical differentiation, we will look at the analytical differentiation of this function and some other function before we now see how to differentiate them numerically. So now, before we go on, I would like to list the functions that I will want to work with on this. So here are the functions that I would like us to work with. So after coming down here, you have to, if I want to write something here, I'll have to tell MATLAB that I'm writing text, not code. So here it is in code mode, and I click the text mode so that I can now type text. So I'm bringing in another function that I call the g of x. So let me use text so that it looks nice. So g of x, and that will be equal to, I'm using x squared and then cosine of x. So that is multiplication. And then after that, I'm going to have another function, insert equation, and that's going to be f of x. And that's x divided by, I have 2 minus tangent of x. So these are the three functions that I'm going to be working with. So we start with the first one. So let us perform the differentiation of the first one. So what will be the differentiation of h of x with respect to x? And here is the function. So we're going to have dh dx, and that will be equal. So here you differentiate the square of cos x respect to cos x. That is differentiating x square respect to x, which is just 2x. So this will just be 2 cos x. And then you differentiate the cos of x respect to x, which is minus sine x. So I have sine x, and then I just put the negative sign in front of it. So that's the differentiation of h with respect to x. So what about the other one? Let's say we want to differentiate the other, which is g of x with respect to x. So you remember the rule that I used here in the differentiation of h. That is the function of function rule. All right. But for the differentiation of g, you have the product rule because you have two different functions multiplying each other. So, and then I have dg dx, and that's in that case I'm just gonna have 2x cos of x, the minus, yes, so 2x cos of x, then I have x squared sine of x. So you know where the minus came from? The minus is from the differentiation of cosine. All right, you differentiate cosine with respect to the x, and then it becomes minus sine x. So let us look at the third one. So we have increasing order of complexity, and then the last one, which will be df, and then dx. Bottom the top minus top the bottom divided by bottom squared. Sorry, the bottom, which is 2 minus tan x. The top, differentiation of the top, which is 1, minus top the bottom, so x, then differentiation of the bottom, which is 2. Differentiate 2, you have 0. Then differentiate tan x. So what do you have? That is sec squared x. All right, then sec squared x. All right. So then you don't need to put this 1. Now, all these are in the numerator. Then divided by the bottom squared. Right. That is the differentiation. So it looks a little bit more complex, but that is it. So when we want to now do the numerical differentiation, like here you can program all these and put the value of any x there, and then you see the results. So, but the beauty of numerical differentiation is that it's just one method that does all kind of differentiation. So here, for the h, we use the method of function of function to do the differentiation analytically. For the G, we use product rule, all right, to differentiate. For the F, we use the quotient rule to do the differentiation. But also remember, it is possible that you have to use the combination of all different techniques to perform the differentiation of a function. But when it comes to numerical differentiation, it's just one method. Now, before we proceed, let me quickly make a correction. So I have double negative sign here when I differentiated this. So a minus sign, which is in the definition, and then another minus sign that is from this minus sign when you differentiated tan to become square squared. So this becomes a positive sign. To now write this differentiation as function handle so that we can evaluate them for comparison for the numerical differentiation that we want to do. So let us start with the h. We differentiated the h, and this is what we got. So we're going to now create a function handle for that. So the h dx equals, so at x, and then we have minus 2 times cos x, then sine x. So let us program other functions and their derivatives. There you have it. Now, you should note that in numerical differentiation, you are not going to be getting the functions like we get here, which are the analytical functions. We are going to be getting numbers that happens to be values of the functions at different values of the independent variables. So, but what we're going to do to compare with what we have here analytically is to evaluate the analytical functions and check if it gives us the same values as what we got from the numerical differentiation. So, having laid the groundwork for how we're going to compare the solution of the numerical differentiation to know whether it is correct or wrong, it is now time to turn our attention to the definition of numerical differentiation. And here we bring in Mr. Newton. So, according to Newton, the differentiation of a function is defined in terms of limits of the independent variable as it approaches zero. So, here is what it says. Let us insert an equation here. So, here I start with first dy dx. Let's say a small h approaches zero, or it's a fraction. Then I have x plus h minus I of x divided by h. All right. So this is the definition. And this definition says as h goes to 0, this expression approaches dy dx. So if x is going to 0, that means we're talking about the instantaneous rate of change of y with respect to s. How it is changing at an instant. So let us put this to test by creating a function that I'm going to call the differentiator. So this helps us to differentiate any function. So let us create that. So it's going to be a function. So I have function, and then this, I'll call it dy dx, and then this is equal to, going to call it differentiator. That makes sense? Yeah, it helps us to differentiate any function. So the function is y, and the point at which I want to compute the differentiation is x. All right. So this y right here is a function handle. So I'm going to now say, okay, and that is to keep that within the scope. So I'm going to declare my h. I say 1 exponent minus 6. Remember, in the definition, Newton says h must be a really small number. It must be approaching 0. So in that case, we have the y dx, and then that is equal to yx plus h, and then minus y of x, and I'm going to divide everything by h. And that is it. So when you hear people say they do numerical differentiation, this is what they're doing. It's just this one line. Of course, there are some little additions, some little modifications that you might need to add, to deal with some cases, but in general, this is what we call numerical differentiation. Now let us see if it works. We are going to put it to test. So here I'm going to be, for us to be able to see them together, I'm going to call the analytical differentiation and the numerical differentiation, and then we are going to put them side by side to see the values to know whether the numerical differentiation that we're doing is correct or not. So let me do a quick recap. I told you that in numerical differentiation, we work with the values. And I told you that for you to get the values, you have to evaluate the function. And I show you how to evaluate the function here. Just call the function handle and then pass the value at which you want to evaluate the function. So I need h at 2, h at 5, and h at 20. So what is happening here? How are we getting the values that we're working on? Well, we are also evaluating the function. So the function here is y, and when it comes in here, I evaluate it at x plus h, I evaluate it at x, then I take the difference and then divide by h. So that means we are actually working with just the numbers, not the function itself. We are evaluating it at the point of interest and then using the values to compute the differentiation at that point. Okay, so let us start by testing age. So I bring in the code, and then now let us test what is the differentiation of age with respect to x, let's say at point 4. So we have the h, the x, we already defined the function, and then I'm going to pass the value 4. And let us run that, this section, and see what we have. Oh, sorry, I have not run this already. So this is not known. So I'm going to run the entire code. And then we got this point. It said, this is the differentiation. The differentiation of h respect to s at 4 is minus 0.9894. Okay, fine. Let us see if we perform the numerical differentiation if we're going to get the same thing. So to do that, I'm going to call this guy the differentiator. So I'm going to say, okay, differentiator, please differentiate h for me at point 4. And then let us run this section to see what we get. Aha! Now, exactly the same number, minus 0.9894. So this guy right here is differentiating the function and giving us exactly the same value at x equal to 4. Remember, I did not program anything that has to do with technique of differentiation here. Just the original definition by Sir Isaac Newton. And then we're getting exactly the same value. Okay, if you are wondering, oh, how? I learned a lot of things to understand how to do differentiation. How can just this small one line be doing everything? Well, let me blow your mind. Let us try to differentiate the other ones. So I'm going to do dg dx. G dx at 4, and then G dx at 4. So let us run the section and see. Aha! Exactly the same thing. Here. So the GDX at 4 is this number, 0. I mean 6.8797, and the same thing for the numerical value. All right. Okay. Let us try another one. Let us try for the F and see if we get the same thing. Okay, for the F, and then let's get here and see what the values are. And we'll find we have 14.3873 and then 14.373, exactly the same value. Okay, somebody might say, oh, why? Are they only correct at 4? Can you try any other number? Okay, now this is why you need to declare your variable. So I'm going to declare a variable. So let me say the variable that I want to use for the different, I call it XX, and I call that, let me give that guy 5, and then I pass that through all of them. So XX, 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 okay, and that. So let us run this section and see what the result is. Fine. So this is the analytical differentiation, the one you did with your knowledge of differentiation. And this is the one I did with just this one line, line 20. So, and then this here is the analytical, and this one is the numerical. And this is analytical, this is numerical. You can see that they are the same. So 4 decimal places. However, there are differences, but the difference may be maybe in the sixth or the seventh decimal places, but not in the fourth decimal. At least correct about 6 decimal places, they are the same. This is what we call numerical differentiation. And thank you for listening. Next time, I will show you the application of numerical differentiation.